As you advance through your physics course, you may notice that physics is more than simply finding formulas and plugging numbers into them. Much of the focus will be conceptual. Why do things move? What happens over time for a rock falling off a cliff? How are two variables related? Fortunately, you always will have a formula sheet and a good deal of math training. You do not have to memorize physics. You simply have to learn how to read the equations as if they're a language. They'll tell you everything you need to know. For most high school physics courses, there are three basic mathematical relationships you should learn to recognize. Let's introduce these three one at a time, starting with the most basic. Most of you will be well versed with the first mathematical relationship. It's called a linear relationship. You may have seen this in your math class written in slope-intercept form, or y equals mx plus b, where m is the slope, or the gradient, of your line, and b is the y-intercept. For a single line, both the slope m and the intercept b will remain constant. What varies are the x and y coordinates of all the points that make up the line. We say that x and y are the variables. For this tutorial, we will focus on a very specific form of the linear relationship where the y-intercept is 0. In other words, our line will pass through the origin with some slope m, which could be positive or negative, depending on the equation. Direct relationships will be written more simply as y equals mx, since the intercept, b, is equal to 0. Let's take a look at a physics equation you will encounter that identifies such a relationship. In kinematics, we have a very basic motion equation that states d, or displacement, is equal to vt. Displacement is equivalent to velocity multiplied by time. We use this for constant velocity questions. Since v is constant, we can see that the two variables, d and t, are on opposite sides of the equation, just like our definition of direct equations where y and x are on opposite sides. Since d equals vt looks the same as our direct relation, it must behave the same way as well. Let's find out. How does d vary with t? One technique is to make up some numbers and see exactly what happens. Let's imagine our velocity, our constant velocity, is 10 meters per second. Let's create a table of values for d and t and plot d versus t on a graph. Let's start at 0 seconds and calculate our displacement d for the next 3 seconds using the equation above. For example, when t equals 0, we know that d is vt, so d would equal 10 times 0, which is 0. When t is equal to 1, we have d is equal to 10 times 1, which is 10, and so on, until we get our table filled out as we see below. When we plot the points on our graph, we see that it creates a straight line that passes through the origin, which is our definition of a direct equation. You may notice that the slope is equivalent to the constant velocity of 10 meters per second. I'll leave it to you to check to see if that's true. Now let's look at some of the properties of a direct relation. Remember, on your formula sheet, this will be any equation that can be expressed as y equals some constant times x. d equals vt shows a direct relationship between displacement and time. When we create a graph of d versus t, we observe a straight line that passes through the origin. Furthermore, if we look at our data table, we can see another useful property of direct relations. We can see that if we double the time, the displacement d is also doubled. If we triple the time, d is tripled. If we half the time, d is halved, etc. This can prove very useful conceptually, especially on exams and quizzes. The next relation we will look at is the basic quadratic relation, y equals ax squared. We see that this is an equation where the variable on the left, y, depends on the square of the variable on the right, in this case x. By now, most of you will be familiar with this general equation, and remember that it will create a parabolic shape that curves either upwards or downwards, depending on the value of the constant a. Let's look at a kinematics equation where the variables distance and time are related in this way. One such equation is as follows. D, or displacement, is equal to v initial times time plus 1/2 at squared, where a is acceleration. We see that the variable on the left, d, depends on the square of the time, t, which is on the right-hand side. For simplicity, let's imagine we start from rest so that our initial velocity, v0, is equivalent to 0. We now see the basic quadratic form we are familiar with. Displacement, or d, equals 1/2 at squared. In order for us to easily determine what type of relation this is, we must first make sure the two variables, d and t, are separated so that they are on opposite sides of the equation. In this case, they already are. No need to do any algebra to separate them. Now we can see that d on the left is related to t squared on the right, just like our basic form above, where y is related to x squared. Once again, let's make up some numbers and see what happens. Let's imagine our acceleration is 6 meters per second squared. If we create a table of values ranging from 0 to 3 seconds, we get the following displacements. Next, if we plot a graph of d versus t for this accelerating object using our table of values, we create a graph that is clearly not straight. In fact, we can see that it curves upwards as predicted by our basic quadratic form, y is equal to ax squared. Let's see how this data behaves for this quadratic, also known as a square relation. If we double the time, the displacement increases by a factor of 4, or 2 squared. If we triple the time, the displacement increases by a factor of 9, or 3 squared. If we quadruple the time, it would be fair to say that our displacement would increase by a factor of 4 squared, which is 16. We say that the displacement increases with the square of the time. In other words, each time interval will cover more distance than the previous time interval. The last relationship we will look at in this tutorial is the inverse relation. This can be written as y equals a divided by x, where a is some constant. We see that the variable on the left, y, is related to the inverse of x, or 1 over x, on the right. We know from our formula sheet that F net equals ma. This equation does not, at first glance, look like the inverse equation above. In fact, we can see that F net is directly related to the acceleration since these two variables are on opposite sides of the equation and look like y equals mx that we saw earlier. However, how are the acceleration and mass related in this equation? To find out, we need to separate these two variables first. Let's get acceleration on the left by isolating or solving for it algebraically. We see that a now depends on 1 over m, just like our general inverse relation above. We can conclude that there exists an inverse relation between a and m. Once again, let's make up some numbers and see what happens. Let's imagine a net force of 100 newtons. If we create a table of values from 10 to 40 kilograms, we calculate the following accelerations for each mass. Next, if we plot a graph of acceleration versus mass, we create a graph that is clearly not straight. We get the curve as shown. In your math courses, you may have already seen this inverse curve. Let's see how the data behaves for this inverse relation. If we double the mass, the acceleration a is halved, or 1 divided by 2. If we triple the mass, the acceleration decreases by a factor of 3, or 1/3 of its original value. Conversely, if we quarter the mass, we will quadruple the acceleration. In other words, if one value increases, the other will decrease, which is why we call this an inverse relation. You may also recall that the vertical and horizontal axes both become asymptotes for such an equation. The graph will get closer and closer and closer to these axes without ever touching them. Let's try it. Substitute a huge mass into our equation. What happens? You should find that the acceleration gets smaller and smaller and smaller as the mass gets bigger and bigger and bigger, but never to 0. Now what happens to the equation if the mass gets close to 0? We can't divide by 0. If we do, we get an undefined acceleration. That simply means the acceleration will get infinitely large, which is not possible. Hence the asymptote on the vertical axis. In this tutorial, we have looked at 3 general forms of equations and their behaviors. We looked at direct relationships, which turned out to be a special case of a linear relation, quadratic or square relationships, and inverse. Most high school physics formulas can be expressed in one of these 3 forms. Identifying which relation is present will help you predict patterns and behaviors between variables. The linear relation is written as y equals mx plus b, with the direct relation simply being y equals mx, where there's no intercept. Any physics equation that looks like y equals mx will have the same characteristics and behaviors. For example, when we looked at d equals vt, we see that the variables d and t can replace y and x. When plotting a graph of d versus t, we should therefore expect a straight line that passes through the origin. We also found that if we double one variable, time in this case, the other variable, displacement, will also double. If we triple the time, the displacement will triple, etc. This will be true for any equation that can be expressed as y equals mx. We then looked at quadratic relations. Quadratics can be written most simply as y equals some constant a, x squared. When graphing y versus x, they will create parabolic shapes opening either upwards or downwards depending on the constant. D equals 1/2 at squared is an equation that matches this form. We see that d and t are separated on either side of the equation, showing us that d is related to t squared. We would expect a graph of d versus t to create a parabolic shape. Furthermore, since d is related to t squared, if we double the time, we quadruple d because time is squared. If we triple t, d is increased by a factor of 3 squared, or 9. Finally, we looked at inverse relationships. These are relations that can be expressed as y is a over x. We saw an example when we solved f net equals ma for a. We observed an inverse relation between a and m since a equals f net divided by m. We would expect a graph of a versus m to generate an inverse shape where the two axes become asymptotes. This is also referred to as a hyperbola. We also saw that if we increase the mass by a factor of 2, the acceleration decreases by 1/2, or 1/2. If we increase the mass by a factor of 3, the acceleration decreases by 1/3, which is the inverse of 3. Learning to identify which relation is present by examining the equation can eliminate the need to memorize graphs and behaviors between variables.